A missile can cross hundreds of kilometers in minutes. The defender may have only seconds to understand what is coming, decide what it is, and stop it. And the weapon being fired may be faster than sound, maneuvering through the atmosphere or arriving from space. So how do you stop something you can barely see before it reaches its target?
Air defense began with a simple problem. The sky had become a battlefield. When aircraft first appeared in warfare, armies quickly discovered that traditional defenses were no longer enough. A fortress could stop an army approaching from the ground, but an aircraft could simply fly over it. The answer was not one revolutionary weapon, it was a system. Observers watched the sky. Searchlights tried to locate aircraft at night. Anti-aircraft guns attempted to predict where moving aircraft would be when shells arrived. Fighter aircraft were launched to intercept them. But there was a fundamental limitation. The defender had to detect the attacker before the attacker reached its target. That made early warning just as important as the weapon doing the shooting. Then came radar. During the Second World War, radar transformed air defense by allowing operators to detect aircraft at much greater distances, including when visual observation was impossible. For the first time, the defender could begin constructing a picture of the sky before an aircraft appeared overhead. This changed the logic of air warfare. Detection, tracking, identification, decision, engagement. These stages would eventually become the foundation of modern integrated air defense. But aircraft were only the beginning. During the Cold War, a new threat emerged: the missile. Unlike an aircraft, a ballistic missile could climb to enormous altitudes, travel at extreme speeds, and return toward its target on a trajectory that could cross hundreds or thousands of kilometers. A new question appeared. How do you defend against something designed specifically to be difficult to intercept? The answer would require much more than a faster missile. It would require an entire technological architecture. Modern air and missile defense is therefore not one weapon. It is a network of sensors, communication systems, command centers, computers, launchers, and interceptors working together. NATO's current integrated air and missile defense framework, for example, combines surveillance, battle management and command and control, active defenses, and passive defenses across different ranges and altitudes. That principle is crucial because the first weapon fired in a missile defense engagement may not be an interceptor. It may be information.
Imagine that a missile has just been launched. For the people on the ground, nothing may have changed yet. There may be no explosion, no visible aircraft, no warning siren. But somewhere beyond the horizon, a sensor may have detected the event. This is the beginning of the engagement. The first challenge is detection. Modern missile defense architectures use multiple types of sensors: ground-based radars, ship-based radars, space-based systems, aircraft, passive sensors, and increasingly, networks that combine information from many sources. Each sensor sees the battlefield differently. A radar may detect an object and estimate its position. Another sensor may provide additional information. A space-based system may contribute early warning. A command network then attempts to combine these observations into a coherent picture. This is called sensor fusion. Instead of treating every sensor as an isolated source, the system attempts to determine what all of them are collectively observing. That sounds simple. It is not. A radar does not automatically know what an object is. It sees returns. Those returns have to be interpreted. Is the object an aircraft, a missile, a drone, weather, debris, a false signal? The faster the object moves, the more important accurate tracking becomes. A missile traveling hundreds or thousands of meters per second does not give defenders much time to correct mistakes, so the system must continually estimate its trajectory. Where is the object now? How fast is it moving? Where might it be in 10 seconds? Where might it be in 30? And most importantly, where will it be when the interceptor reaches it? In shift to high curiosity. Because missile defense isn't really about chasing a missile, is it? It is about predicting where the missile will be. That distinction explains much of the technology behind modern interception. A defender does not simply fire an interceptor at the target's current location. The interceptor must meet the target at a future point. This becomes increasingly difficult as the target becomes faster, more maneuverable, or more unpredictable. And different threats require different solutions. A small drone flying slowly at low altitude is a very different problem than a ballistic missile descending from the upper atmosphere. A cruise missile is different again. It may fly relatively low, use terrain to hide from radar, and approach from an unexpected direction. A ballistic missile may follow a high-speed trajectory through the atmosphere and potentially beyond it. This is why modern defense is layered. One system cannot efficiently handle every threat. Instead, different systems are designed for different portions of the problem, in shift to cold and authoritative. At the short-range end are systems designed to protect specific areas against aircraft, drones, rockets, or other low-level threats. Further out are medium and long-range systems. And against certain ballistic missile threats, specialized interceptors are designed to engage targets at much higher altitudes. The principle is redundancy. If one layer fails, another may still have an opportunity. NATO's current IAMD policy explicitly describes this layered approach, combining systems operating at different ranges and altitudes to increase defensive effectiveness and provide redundancy. This architecture is particularly important because no interceptor is guaranteed to work every time. That may sound obvious, but it creates a major strategic problem. If an attacker launches one missile, a defender may have a reasonable opportunity to respond. But what happens when dozens arrive together, or hundreds? This is where missile defense becomes an economic and logistical contest. An interceptor is an expensive piece of technology. A missile designed to overwhelm defenses may be significantly cheaper, and an attacker does not necessarily need every missile to get through. If even a small percentage penetrates, the consequences can still be severe. This creates the concept of saturation. The defender is not simply trying to destroy missiles. The defender is trying to maintain enough detection, processing, launcher capacity, interceptor inventory, and decision-making capacity to continue fighting through repeated attacks. That is why modern air defense is as much about architecture as it is about individual weapons. In shift to dramatic pause and secretive, the interceptor itself is only the final step. Before it launches, the system must know where the threat is. Before that, the system must know that the object is actually a threat. And before that, the system must have enough warning to react. This brings us to the heart of the revolution: command and control. A modern air defense network is essentially a race against time. Sensors generate information, computers process it, command systems prioritize threats, operators or automated systems determine responses, launchers fire. The interceptor then searches for the target and attempts to destroy it. Every stage consumes time, and every stage can fail. In shift to high energy and explosive, which means the most advanced air defense system in the world can still be vulnerable if its sensors are blinded, its communications disrupted, or its decision-making overwhelmed. This is why integration matters so much. A radar does not need to be the same system as the launcher. One sensor may detect the threat, another may track it,
A command system may calculate the engagement solution, and a completely different interceptor may perform the final attack. The network connects them. That is the real technology behind modern air defense. Not a single missile, a chain.
To understand the sophistication of this system, consider what the defender is actually trying to accomplish. The first task is awareness. The system needs to know what is happening in the airspace. The second is discrimination. It must determine which objects matter. The third is tracking. It needs a reliable estimate of where the threat is going. The fourth is decision-making. The system must determine which defensive response is appropriate. The fifth is engagement. An interceptor must actually reach the target. And the sixth is assessment. Did the interception work? If not, is another engagement necessary? This creates a continuous feedback loop. The system is constantly updating its understanding of the battlefield. And this is where computing power becomes essential. A modern air defense network can process enormous amounts of information much faster than a human organization could manually. Algorithms can help identify patterns. They can help prioritize contacts. They can assist with trajectory prediction. They can help operators distinguish between different types of threats. And artificial intelligence may increasingly contribute to this process. NATO's 2025 IAMD policy explicitly identifies advanced algorithms, machine learning, and potentially artificial intelligence as tools that can support surveillance data fusion and analysis. But AI does not magically solve the underlying problem. It still depends on sensors. It still depends on communications. It still depends on data. And it still operates inside a physical environment governed by physics. That last point is easy to overlook. A computer can calculate a trajectory almost instantly, but an interceptor still has to travel through the atmosphere. Its engine has limits. Its sensors have limits. Its maneuverability has limits. The target may also maneuver. So missile defense is ultimately a battle between prediction and uncertainty. The defender predicts where the target will be. The attacker tries to make that prediction harder. This has produced an endless technological competition. As defenses improve, offensive weapons evolve. As missiles become more accurate, defenses become more sophisticated. As radar becomes more capable, attackers develop methods of reducing detectability. As interceptors improve, attackers may use maneuvering, multiple warheads, decoys, or coordinated attacks to complicate interception. It becomes an evolutionary contest. But if both sides keep adapting, can any air defense system ever become truly impenetrable? The answer is almost certainly no. Modern missile defense is not a perfect shield. Its objective is to reduce risk. That distinction matters. A defensive system does not necessarily need to stop every missile. It may still be strategically valuable if it reduces the number of successful attacks enough to protect critical infrastructure, military forces, or population centers. This changes how we should evaluate defensive technology. The relevant question is not simply, can it stop a missile? The more useful question is, under what conditions, against what threat, and at what scale can it reduce the damage? That is a much harder question, because performance depends on the entire engagement environment. Threat type, range, altitude, speed, trajectory, weather, sensor coverage, electronic warfare, number of incoming weapons, interceptor availability, and the quality of information available to the defenders. This is why test results should be interpreted carefully. A successful interception under controlled conditions demonstrates a capability. It does not automatically prove that the same system could defeat a large, sophisticated attack under wartime conditions. Real combat introduces uncertainty that laboratories cannot fully reproduce. There is another important issue. Air defense can never be separated completely from offense. A country may build defenses to protect its territory, but those defenses can also influence an adversary's calculations. If an attacker believes its missiles are unlikely to penetrate, it may reconsider an attack.
That means missile defense can function as part of deterrence. But there is a complicated strategic problem. If a country believes its defensive shield is extremely strong, it might also become more confident in taking risks elsewhere. And if an adversary believes that its missiles are being neutralized, it may search for alternative methods of attack. This creates an interaction between offense and defense. The technological competition, therefore, never ends.
Different air defense systems reflect different answers to the same fundamental problem. The United States has developed a broad family of systems covering different threat classes and ranges. The Aegis system uses powerful ship-based radar and interceptors and has also been adapted for land-based ballistic missile defense. Patriot provides another layer, particularly against aircraft and certain missile threats. Israel has developed a highly layered architecture that includes systems designed for different categories of threats. Iron Dome focuses on short-range rockets and other threats. David Sling addresses a different portion of the threat spectrum. Aero systems are designed for ballistic missile defense. The lesson is not that one system is universally superior. The lesson is that different threats require different engineering solutions. A short-range rocket presents a different engagement problem from an intercontinental ballistic missile. A low-flying cruise missile presents a different problem from a ballistic missile traveling through the upper atmosphere. This is why comparing air defense systems by asking which one is best can be misleading. The more useful comparison is between missions. What threat was the system designed to address? At what range? At what altitude? Against how many simultaneous targets? With what sensors? And inside what larger network? NATO's architecture illustrates this broader approach. Its integrated system combines national and multinational sensors, command and control, air defense systems, and ballistic missile defense capabilities, rather than relying on one universal interceptor. That is perhaps the most important lesson. Modern air defense is no longer a weapon, it is an ecosystem.
The biggest mistake would be to imagine that modern air defense has made missile attacks obsolete. It has not. There are fundamental limitations. The first is physics. A fast-moving target gives defenders less time to react. The second is geometry. A radar cannot see equally well in every direction at every altitude. Terrain can block low-altitude threats. The curvature of the Earth limits line-of-sight detection. The third is complexity. A missile attack may include different weapons arriving along different trajectories. Some may fly high, others may fly low. Some may maneuver, others may be designed to create confusion. This makes classification and prioritization extremely difficult. The fourth limitation is capacity. Every defensive system has finite resources, finite launchers, finite interceptors, finite radar capacity, finite personnel, finite ammunition, and finite time. An attacker can attempt to exploit those limits through mass. This is why saturation is so important. The fifth limitation is electronic warfare. Modern air defenses depend heavily on communications and electronic systems. An adversary may attempt to disrupt those systems without physically destroying them. Jamming, cyber attacks, deception, electromagnetic interference. These can create problems for a network that depends on information arriving accurately and continuously. NATO's current policy explicitly recognizes the need for resilience against cyber attacks and electromagnetic warfare, emphasizing redundancy and distributed command and control structures. Then, there is the problem of cost. Missile defense can become an expensive game. An interceptor may cost substantially more than the threat it destroys. If a defender repeatedly uses expensive interceptors against inexpensive drones or rockets, the economic balance can become unfavorable. That is why the future of air defense is moving toward a wider range of responses. Not every threat requires the same interceptor. Some may be addressed with electronic warfare, others with guns, others with cheaper short-range interceptors, others with high-end missile systems, and potentially, in the future, directed energy weapons. The objective is to match the cost and capability of the defense to the threat. Because the future battlefield may not be decided by the country with the most advanced interceptor, it may be decided by the country with the most efficient defensive network.
This technology is no longer theoretical. Recent conflicts have demonstrated how central air and missile defense has become to national security. The war in Ukraine has shown the destructive potential of large-scale missile and drone campaigns, while also demonstrating the importance of layered defenses. NATO has described integrated air and missile defense as a continuous mission and has expanded its focus on threats from small drones to cruise missiles and ballistic missiles. In 2026, NATO also stated that its ballistic missile defense capability had identified, tracked, and intercepted ballistic missiles launched from Iran toward Turkey, and subsequently increased its alliance-wide missile defense posture. These developments reveal something important. The definition of air defense is expanding. It is no longer only about protecting cities from aircraft. It includes drones, cruise missiles, ballistic missiles, hypersonic threats, electronic attacks, space-based sensors, and the information networks connecting them all. Artificial intelligence may become increasingly important in this environment. Imagine an air defense network receiving thousands of sensor observations simultaneously. A human cannot manually compare every signal. An algorithm can. It can search for patterns, predict trajectories, identify anomalies, prioritize threats, and present decision-makers with a clearer picture. But this creates a new challenge. The more sophisticated the network becomes, the more dependent it becomes on software. And software introduces its own vulnerabilities. A system can be technically advanced and still fail because its communications are disrupted, its assumptions are wrong, or its data is incomplete. The future, therefore, belongs neither entirely to machines nor entirely to humans. It belongs to the interaction between them. Humans provide judgment. Machines provide speed. Sensors provide information. Networks connect the pieces. Interceptors provide the physical response. And the entire system depends on every layer functioning well enough for the others to matter. So perhaps the real revolution in air defense is not the interceptor at all, but the invisible network that tells it where to look. For most of history, protecting a nation meant building walls, armies, and fortifications. Modern air defense has replaced the wall with something far more complicated. A network that sees, calculates, predicts, decides, and responds in seconds. But no system can guarantee perfect protection. Every new defense creates new incentives for attackers to adapt, and every new missile forces defenders to rethink the shield. The future will therefore not be a simple contest between missiles and interceptors. It will be a contest between entire systems. As weapons become faster, smarter, and harder to predict, will the future of security depend on building an impenetrable shield or simply becoming better at surviving what gets through? Share your thoughts in the comments, like the video, and subscribe for more in-depth documentaries.